Hi, this video is on annuities in advance and arrears. It's on the sequences and series unit of General Maths 3. We're learning to model annuities in advance and arrears using difference equations, and by the end of this video you should be able to identify when a situation can be described as an annuity, when it's in arrears, when it's in advance, and hence choose the right equation, as they're slightly different depending on which one it is. You should be able to sub in values and use your CAS calculator to solve problems. So typical examples of annuities: saving for something and making a monthly payment. A superannuation fund where you contribute money every fortnight. A mortgage where you borrow money, for example to buy a house, and make regular payments back. And a personal loan where you make a regular fixed payment each month. Now the thing that all of these have in common is the regular payment. That's what makes it an annuity. But they're slightly different because these first two are examples where you put money in first in advance and then get a big pot of money at the end, and all the while that you're making your payments, it's growing because interest is being applied to it. You give your money and let it sit in the bank, and the bank gives you interest payments. So if the payments come in advance, then that's annuities in advance. These two are a bit different. You get the money up front from the bank, then they charge you interest on the money that you've borrowed, and then you make payments back regularly. So the money's up front, the payments come afterwards. So this is in arrears. Sadly, this is what we typically have more to do with because we're borrowing money off the bank in order to pay for a car, to go on holiday, to buy a house, and very important that we all do this and this as well. But you'll see how it all works in the next couple of slides. Now, annuities in advance. The regular payments are in advance of the big pile of money. So an example would be paying into a savings account or superannuation contributions. You pay your money in, pay your money in, pay your money in, pay your money in. All the time it's growing as the interest gets applied to it, and you finish with a big pot of money. Very nice. In arrears is where, for example, you borrow the money from the bank and then make a payment until the debt is gone. And all the time the amount you owe them is going up as well because interest is being applied to it. So there we go, getting a mortgage. Now another thing's getting your superannuation. So if you have a big pot of money saved up, you then take money out of it until it goes down to zero. A combination of both would be a superannuation rollover. You pay your money in for 40 years as you're working, you save up a big pot of money, and then take money out as you go. Okay, annuities and arrears can be modelled using a difference equation. So what we do is we borrow a certain amount of money, which actually I'm going to call T0. So our initial loan here, T0, is how much we borrow. Then there's an interest rate applied to it. So as soon as you borrow the money, the bank whacks it up immediately and says, okay, you owe us more than you used to. That was before you get to pay anything off, and then you make a payment and it comes down a little bit. The interest rate is 1 plus I because it's percentage increase. This is how much our regular payment is, and this is what we owe afterwards, our account balance. So ultimately we want this to come down to zero so we don't owe the bank any more money. So a loan of $10,000 is taken out. That's our initial loan at an interest rate of 9.1%. Now this is compounded fortnightly. That's important. What the bank does is it applies the interest more frequently than just once a year. It applies it every 2 weeks in this case. So instead of applying 9.1% every 2 weeks, which would make it grow very, very quickly, what they do is they take their 9.1, which is 0.091, and divide it by 26. So divide it by the number of bits it wants to split it into. It's going to do it every fortnight, so that's 26 times a year. So 0.091 divided by 26 gives us 0.0035. That's our interest rate, but it's 1 plus that because it's percentage increase. Situation can be modelled by the difference equation then. 1.0035, which is our interest rate, multiplied by the previous term minus the amount we're paying off the debt. Our initial T0 is 10,000. Over here we can see the table, number of payments made, account balance, so how much we owe. So after 20 payments have been made, the balance is 8,741. That's how much you still owe. Okay, so this is an example of annuities in arrears because we have the money up front, a bank loan, and we're paying it off afterwards. So the money is up front and then the payments come after, so it's arrears. Here's our interest rate. It's calculated each month, and monthly repayments are there. So we have all the information we need to set this up. Monthly interest rate, okay, 0.08, but it's divided by 12 because it's monthly, and that equals 0.00666667. Use lots of decimal places in these calculations because if you don't, your answers they'll be affected by the compounding and we won't end up with an accurate answer. So plenty of decimal places, please. Difference equation rather. So what we're going to have is Tn plus 1 is equal to 1.006667 multiplied by Tn minus our regular payment of 114.68. Remember, this is 1.006667 because it's percentage increase, and then this is our regular payment. Now T0 is how much we start with, and we owe 12,000. Use your equation to generate the first four terms. So use your calculator. Now you can see I've already typed it in here. I've got an plus 1 in my recursive sequence, 1.00666667 times the nth term minus 114.68 rather. Now I'm using A0 as I said before, which you can select from here. You can do A0 there. And I'm starting at 12,000. Now, to see this in the table down here, go to your XY here. I'd start at 0, and I probably don't need to go that high. Maybe 200 payments will do. We'll have a look and see. And then click on that, it generates the table of values. So, first four terms, I start with 12,000, and you can see here's the first one, second one, third one, and fourth term there. Now, it's interesting to note that even though you've made a payment of $114, you've actually only, if you look here, paid off $35 off the amount that you owed. And that's because the bank applies interest straight away, so they've increased that 12,000 by increasing it by this 0.00667, then taken off that, which means that what would it be? About $80 or so would be interest at the beginning. Okay. Prepare your calculator to copy a graph which models the amount in the account. So click on your graph here. We want AN, not the sigma, not for this one. Now, mine's come up like this because I've already gone in and had a look at this and fixed up my view window. I want to go up to 12,000 on the y-axis because that's where I start from, so a little bit above, a little bit below 0 because I'm paying it down to 0. And I already had a look down the table and noticed that by 180 I paid a loan off, it goes to 0, so I've set it up to 185. And it comes all the way down to there. So this is what it looks like. Excuse me. And loan balance, and this is number of payments down here. Over here on the next page, excuse me, there we go. How long will it take before the loan is repaid? What you want to do is have a look down your table to see, well, when does it actually get down to 0? And here we go, you can see 160 there. A bit further down, 170, it's getting down into the hundreds. So we owe 450, 338, 226, 113, 0. So 180 payments in total. So yes, on the 179th payment we owed 113, the 180th payment we owe 0. Actually, the bank would owe us 59 cents if we paid that in full. So our last payment would be a little bit less than that, 114. 180 payments, but remember 180 payments is 180 months, so okay, so 120th, there we go, so 565,540. That's how much we owe after 10 years. Okay, now the next one is annuities in advance. So this is where, for example, we are making payments in advance and save up a lump sum at the end. So the formula, you'll notice, looks a little bit different. We start usually with 0 and then add in a regular payment, and then interest gets added onto that afterwards. So in here, add the payment, interest applied. Same rules apply to the rate, so it's 1 plus I, and compounding works in the same way. So it's monthly, it means we take our 0.066 and divide by 12. Then it becomes 1 plus that, so 1.0055 is our interest rate here. That's our account balance again, that's our regular deposit. So our account balance is equal to the interest rate multiplied by our nth term plus 150, which is our regular amount we're saving. Start with 0. I'm going to change that to 0 again. Now, the amount, say after 10 years, where n is 120 interest periods, can be found using the sequence mode of the calculator. So okay, so clear the old one. We'll have a look in here. We've got 1.0055 multiplied, open your brackets, by the nth term, which we'll find there, an plus 150. Close your brackets. Our 0 term here is 0. We're starting with nothing and we're saving money. There we go. We can generate the table there and see that after 10 years there's 120 interest payments. Down here, where are we? There we go. $25,539. Now I should say we should click in there and we can see underneath actually 25538.69 as it says here. Okay. Now here's an interesting thing. If you open a savings account but you actually have some money to put in the first part that's more than your regular payment, you can do that still using the same situation. Here we've got Rachel decides to kickstart her account with an initial deposit of $1,000. But rather than put $1,000 in as T1, that 1,000 takes into account your initial. We're saying we have a regular deposit of 150. So if you had 850 and 150, that would make your first 1,000 that you've got, and then it's 150 thereafter. Okay, we're going to show that the amount after 120 is 27,000 if you put that extra bit in. So 850 goes into there, AM plus 150 there, and recalculate. And if we go down to 120, we'll see. Oh, there we go. 27,782.58. So considerably more money than she had before for that extra initial deposit. That's because compound interest makes it grow exponentially. Okay, here's an example of annuities in advance. City Cafe is budgeting for renovations in 6 years' time, so they're saving up for it. So they save, and then they have money at the end. Use a difference equation to model the amount in the account. So Tn plus 1 is equal to R Tn plus D T0 equals initial amount. Tn plus 1 then is going to be equal to, now it's 5.2% fortnightly, so we need to do a bit of side working. 0.052 divided by 26, which is 0.002. Remember that becomes 1.002 now. Tn plus 50. T0 is 0. How much in the account after 6 years? Okay, so we've had 6 years worth of payments every fortnight. 6 times 26 is 156. So n is 156. That's what we look up in our table. Have a look at the sequence mode, generate the table, and there we want to go to the 156th. Click in that and you can see that it's 9,161 and 51 cents. What if instead you started with $800? Well, rather than put 800 there, we put in 750 because 50 of it is in our regular payment. Recalculate and go back to 156. And you can see here it's 10,185 and 81 cents. Quick recap, it's annuities if there are regular payments. It's annuities in advance if the payments come first, such as putting monies in savings. Payments come after is annuities in arrears, such as when you borrow money for a car. And to find the interest rate, you divide the decimal interest rate by the number of compound periods per year.